Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, going to deliver a topic, Magnetostatics, under the subject Applied Electronics and Instrumentation in BTech Agriculture 4th semester. So, magnetostatics, that is, uh, statics means uh, the charge at rest, or magnetostatics is a topic which is related with the magnetic effect of uh, moving charge, or normally if I want to talk about some magnetostatics, that is the magnetic field of any or whatever, what is the magnetic behavior of any magnetic material. So magnetostatics having have very wide applications and very wide role in the industrial use and the day-to-day use also. So we are starting with the magnetostatics. What we will learn about magnetism, there are not poles and south poles. Like poles repel, unlike poles attract. Magnetic force attract only magnetic material. Magnetic forces act at a distance, while magnetize, temporary magnets act like permanent magnets. So just this is due to the uh, dipoles exist in the materials, and due to the behavior of the dipoles, there are some changes in the effect of other magnets. So now, for every north there is a south. Every magnet has at least one north pole and one south pole. By convention, we said that magnetic field lines leave the north end of magnet and enter the south end of magnet. If you take a bar magnet and break it into two pieces, each piece will again have north pole and south pole. If you take one of those pieces and break into two, each of the smaller pieces will have north pole and a south pole. No matter how small the pieces of the magnet become, each piece will have north pole and south pole. No monopoles allowed. It has not been shown to be possible to end up with a single north pole or single south pole, which is monopole. Mono means one or single, thus one pole. Note, some theorists believe that magnetic monopoles may have been made in early universe. So far, none have been detected. Magnets have magnetic fields. We will say that moving charge sets up in the space around it magnetic field, and it is magnetic field which exerts a force on any other charge moving through it. Magnetic fields are vector quantities, that is, they have magnitude and direction. Magnetics. A magnet attracts or repels another magnet. This gives us the first observable interaction in the magnetic field. It also attracts a piece of iron. It will not attract the piece of copper. Conclusion, there are different types of material in the terms of their magnetic properties. The magnetic properties are governed by the permeability of the material mu, that is Henry per meter. The strength of the magnetic field is usually given by the magnetic flux density B, uh, SI unit is Tesla. The magnetic flux density is also called magnetic induction. The magnetic field intensity H, that is SI unit is Ampere per meter. The relationship between the two is very simple. B is equals to mu naught mu R into H. Mu naught is equals to 4 pi into 10 to the power minus 7 Henry per meter is the permeability of a vacuum. Mu R is the relative permeability of the medium in which the relation holds. In which the relation holds. Mu R is given as the ratio between the permeability of the medium and that of vacuum, a dimensionless quantity associated with each material in nature. Permeabilities of some useful materials are given next. Magnetic materials uh, having mu are less than 1 are known as diamagnetic, and if any material is having mu are greater than 1, they are known as paramagnetic. And the ferromagnetic, whose permeability is very greater than 1, iron like, the latter are often the most useful materials when working with the magnetic fields. There are other types of magnetic materials: ferrites, magnetic powders, magnetic fluids, magnetic glasses, etc. Magnetostatics: if charges are moving with constant velocity, a static magnetic or magnetostatic field is produced. The magnetostatic fields originate from currents. For instance, direct currents in current varying wires. Most of the equations we have derived for the electric fields may be readily used to obtain corresponding equations for magnetic fields if the equivalent analogous quantities are substituted. By Biot-Servor's law, the magnetic field intensity mm, dH produced at point P by the differential current element IDL is proportional to the product of IDL and the sine of the angle between the elements and the line joining P to the element, and is inversely proportional to the square of the distance r between P and element in SI unit. So, using the definition of cross product, we can represent the previous equation in vector form as the direction of can be determined by the right hand rule or by the left hand screw rule. Uh, if the position of the field point is specified by and the position of the source point by, where is the unit vector directed from the source point to the field point and is the distance between these two points. Charged particles. So the electrically charged particles are moving in the, we are talking about the electrons. When the electrons are in the motion, they exhibit the magnetic field. Examples include the spin of a proton and the motion of electrons through wire in electric circuit. When magnetic field actually consists of is somewhat of a mystery, but we do know it is a special property of space. In atoms containing many electrons, the electrons usually pair up with all the spins opposite to each other so that their field cancel each other. Hence, most substances are not magnets. However, for certain strongly magnetic materials such as iron, cobalt, and nickel, the magnetic field produced by the electron spin do not cancel completely. Such strong magnetic materials whose spins do not completely cancel uh, are said to be some ferromagnetic material. In these materials, there are a strong coupling between neighboring atoms to form large group of atoms where spins are aligned and called as domain. The classification of magnetic material is done on the basis of orientation of electronic or electron spins. The magnetic properties of many materials are explained by the fact that the electron also spins to its axis like a top as it circles in its orbit. A bar magnet establishes a magnetic field H in space. A magnetic field is also produced by a solenoid, a long wire closely wound in a helix carrying a direct current. When the inner air space or of the solenoid core is filled with the iron bar, the external magnetic field strength is dramatically amplified. The two basic relationships which help us to calculate magnetic field for a given configuration is Biot-Servor's law and Ampere's law. What the Biot-Servor's law says? A Biot-Servor's law says steady current in a wire has a magnetic field associated with it. The field, which are lines of force or magnetic flux, can be plotted with the compass and has direction as given by the right hand thumb rule. If the current flows in the thumb direction, then the magnetic lines are in the direction of closing figures of right hand. The field is expressed as magnetic field intensity at H point. The Biot-Servor law states the magnetic field intensity at point P due to the current element I dt is given by dH is equals to I dt into 1 r upon 4 pi r square. The Biot-Servor's law may also be expressed in terms of distribution resources such as surface current density and current density J. Now, the Ampere circuital law says that field intensity at the point distance r from a long straight filament conductor carrying current I is given by H equals to I upon 2 pi r. If we take H integral around a closed path with radius r enclosing the conductor once, this relationship holds for all cases over single closed path. So the concept of magnetic field and the magnetic flux of line uh, are given by the Biot-Servor and the Ampere circuital law. In magnetic field, two principal quantities are magnetic field intensity and magnetic flux density. B. We have discussed Biot-Servor law and Ampere's law in terms of H or in magnetic field intensity, but these laws can also be put in terms of magnetic flux density, that is B, where during calculation of magnetic field intensity, the surrounding medium is not taken in account, while the calculation of magnetic flux density, the medium need to be considered. The powerful relationship is put in the form magnetic field intensity is equals to mu h, B equals to mu h, where mu is the permeability of the material or a medium. So next, what a magnetic field actually consists of is somewhat of a mystery, but we do know it is a spatial property of space. Magnetic field or lines of flux of moving charge particle. The diagram is showing the magnetic field or lines of flux. Lines of flux or flux magnetic field of lines are the imaginary lines, and by the help of a Biot-Servor law experiment, we come to know that there is a magnetic effect. Uh, Next, name of poles. The lines of magnetic flux flow from one end of the object to the other by convention. We call one end of the magnetic object the north or N seeking pole and the other the S or south seeking pole. As related to Earth's north and south magnetic poles, the magnetic flux is defined as moving from north to south. This is most important line. The magnetic flux, that is the direction of flux line, is from north to south. The Earth does not follow the magnetic configuration in above illustration. Instead, the line of flux are opposite from moving charge particles. Magnets, although individual particles such as electron can have magnetic field, larger objects such as a piece of iron can also have magnetic field. As a sum of the fields of its particles, if a larger object exhibits a sufficiently greater magnetic field, it is called magnet. Magnetic force, the magnetic field of an object can create a magnetic force on other objects with magnetic fields. That force is what we call magnetism. When a magnetic field is applied to a moving electric charge, such as a moving proton or the electrical current in a wire, the force on the charge is called a Lorentz force. Attraction, when two magnets or magnetic objects are close to each other, there is a force that attracts the poles together. The figure showing magnets also strongly attract ferromagnetic materials such as iron, nickel, and cobalt. Force attracts north to south. That is, like poles repel each other, and like poles attract each other. Repulsion: when two magnetic objects like poles facing each other, the magnetic force pushes them apart. Force pushes magnetic objects apart. Illustrated in the figure. Magnetic and electric fields. The magnetic and electric fields are both similar and different. They are also interrelated. Electric charges and magnetism similar. Just as the positive and negative electrical charges attract each other, the north and south pole of a magnet attract each other. In electricity, like charges repel, and in magnetism, like poles repel. Electric charges and magnetism different. The magnetic field is dipole field. The magnetic field is a dipole field. That means that every magnet must have two dipoles, or magnetic dipole. In detail, we can say that the magnetic field produced by a small current loop is similar to the electric field produced from a small electric dipole. For this reason, a small current loop is called magnetic dipole. Its dipole moment is defined as equal to the product of the area of the plane, loop, and the magnitude of the circulating current. The vector direction of the dipole moment is perpendicular to the plane of the loop and is along the direction of the right hand screw when moved in the direction of current in the loop. So dipole moment is equals to current in the loop into area of the loop. For circular loop, dipole moment as shown will in the next slides. On the other hand, a positive or negative electrical charges can stand alone. Electrical charges are called monopoles since they can exist without the opposite charges. Magnetic flux density. If the total number of lines of force comprising the magnetic field is called the magnetic flux, and we had already discussed that magnetic flux density and magnetic flux intensity. So magnetic flux density is defined by B. Then the magnetic flux density is defined as the flux is passing per unit area with a material through a plane at right angles to the flux. Classification of magnetic material. Now we are start with some classification of magnetic material. Diamagnetism. Before to the classification, if I just give the small introduction about magnetization. All media materials are affected by the presence of magnetic field. In that, they are found experimentally to acquire magnetic dipole moments. The magnitude of magnetic dipole moment per unit volume is called magnetization. So, that is called the magnetization of the medium and is described by some letter capital M in some standard books known as Ampere per meter. When magnetic field is applied to the material, the magnetic induction flux density is the sum of the effect on vacuum and that on material. So some equations are to be drawn up, which are not in the slide, but I'll let you know. verbally. B equals to mu naught H plus mu naught M is equals to mu naught mu R H, where then M is equals to mu R minus 1 into H and is given as susceptibility into H. Now I introduce one more term, that is susceptibility. So a dimensionless quantity, susceptibility is a dimensionless quantity. Now, classification of magnetic material. With respect to their magnetic behavior, with respect to that of magnetic behavior, materials may be classified as diamagnetic, paramagnetic, ferromagnetic, anti-ferromagnetic, and ferrimagnetic. Briefly, the manifestation of magnetic behavior may be attributed to electron orbital motion, to electron spin, and to nuclear spin. These are the some basic characteristics. On behalf of that, we are going to classify the magnetic materials, that is their behavior attributed to electron orbital motion, to electron spin, and to nuclear spin. All the three of these causes are respectively representatively or representable by equivalent atomic current flowing in circular loops. These atomic currents are bound to the individual molecules. These equivalent atomic currents produce magnetic fields, and the aggregate effect of the atomic currents in all the molecules of the material specimen may be to the produce significant macroscopic field. The equivalent atomic current loops are characterized by their magnetic dipole moments. Diamagnetism. Diamagnetism is the property of an object or material that causes it to create a magnetic field in opposite or in opposition to an externally applied magnetic field. Dia means I just relate it with difference or far away. Diamagnetism is the property of an object or material that causes it to create a magnetic field in opposition to external applied magnetic field. It is a quantum mechanical effect that occurs in all materials. Where it is the only contribution to the magnetism, the material is called a diamagnet. Unlike a ferromagnet, a diamagnet is not a permanent magnet. The diamagnetic substance, when subjected to a non-uniform magnetic field, move from stronger to weaker part of the field. Example, when a diamagnetic liquid like water or alcohol in a watch glass is placed over two different poles so apart, the liquid concentrates at the center as the field is minimum at the center. You just seen the slide? A diagram is showing you in which a diamagnetic material is put up and placed on two poles, and you find that the material is more concentrated in the center. So we just back to the statement once again. Unlike a ferromagnetic, a diamagnet is not permanent magnet. The diamagnetic substance, when subjected to non-uniform magnetic field, move from stronger to weaker part of the field. Then The water alcohol in a watch glass is placed over two different poles so apart. The liquid concentrated at the center of the field is minimum. As we know that the field is minimum at the center. Next, paramagnetism. So, before starting the paramagnetism, I just would like to conclude diamagnetism once again. Diamagnetism has its origin in the circular charges in the orbits, and hence all the material exhibit diamagnetism. On the other hand, only those materials which possess permanent magnetic dipoles can be ferromagnetic, anti-ferromagnetic, or ferrimagnetic. When the individual dipoles do not interact with each other and are randomly distributed in the absence of the field, paramagnetism arises. In other three magnetic behaviors, there is sufficient interaction between neighboring dipoles. If the interaction leads to the parallel alignment of neighboring magnetic moments, ferromagnetic behavior is exhibited. In case the result is anti-parallel spin arrangement. And now I'll show the more briefly. Diamagnetic is a substance which exhibits, so to speak, negative magnetism. For diamagnetic, susceptibility is less than 1. Susceptibility is negative and independent of the intensity of the external magnetic field and of temperature. Such materials are magnetized opposite to the direction of the external field, and because of that, they are pushed out of regions of the highest field intensity. The physical origin of diamagnetism can be seen from the classical model of an atom. It may be noted from the equation that the dipole moment introduced in the atom by magnetic field is opposite to it. Although the model is crude when compared to quantum mechanics model, but the calculation of magnetic moments give results which almost agree with quantum deduction. So next, paramagnetism. It may be defined as a type of magnetism in which the material gets weakly magnetized in the same direction as that of applied magnetic field. The material which exhibit paramagnetisms are alkali metals, transition metals, and the rare earth metals or elements. The origin of paramagnetism arises from the presence of magnetic material or magnetic moments in the atoms or molecules. The permanent magnetic moment in a single atom are created due to the moving of the electron is in a circular or elliptical orbit around the nucleus. The motion of an electron is about its own axis spin. It has been observed that the magnetic moments created due to an orbital motion of the electron disappears due to the effect of the electrical field of the neighboring charges. But magnetic moments due to the spin motion of electrons remain unaffected by this field. It will be interesting to add that the spin magnetic moments are composed of two groups. One of the group contains electrons with clockwise spin and the other with anticlockwise spin. In the absence of an electric field, these magnetic moments are randomly distributed, or in other words, they have no mutual interaction among them. This is called paramagnetism. In presence of magnetic field, the moments have a tendency to turn towards the direction of the field. If no opposing forces act, a complete alignment of the atomic moments will produce, and the sample as a whole acquires a very large magnetization in the direction of the field. However, Thermal agitation of the atoms opposes this tendency and tends to randomize the atomic dipole moments. The results are only a partial alignment in the field direction, and hence paramagnetic material exhibits weak inherent magnetization and a small positive susceptibility, or it can be negative. An increase in thermal energy will be increase the randomizing the effect on alignment of magnetic dipole along the field direction and hence decrease the susceptibility. Properties of paramagnetism. Just a minute. Just a minute. Yes. Sorry. Properties of paramagnetism. A paramagnetic material, when placed in a magnetic field, acquires a fibular magnetization in the same sense as the applied field. Platinum, aluminum, copper, sulfate, and nickel are the example of paramagnetism. These substances, when exposed to a non-uniform magnetic field, experience an attractive force towards the stronger part of the field. For example, if we place some paramagnetic liquid in a watch glass and place it over a non-uniform magnetic field, the liquid moves towards the poles as the field is strongest near the poles. The paramagnetism is just opposite to the entirely different or entirely opposite to the diamagnetism. Next, this is the pictorial representation of paramagnetic material. When a uniform and non-uniform electric fields and the paramagnetic material is placed between the field, you find it that the magnetic material move towards to the ends of the poles where the magnetic field of lines are much stronger, so it is more attracted towards the uh, stronger field. So these type of materials are known as paramagnetic material. When paramagnetic materials are placed in uniform magnetic field, the magnetic induction becomes more than the magnetizing field, and thus the relative permeability is slightly greater than unity. The paramagnetic susceptibility is, however, small but positive. The susceptibility is small but it is positive, not less than 1 or negative in the case of diamagnetism. The susceptibility is inversely proportional to the operating temperature. Thus, with the increase in temperature, the X value decreases and susceptible value decreases and becomes negative at elevated high temperatures to exhibit diamagnetic property. So the susceptibility is inversely proportional to the operating temperature. As you are going to increase the temperature for paramagnetic material, the susceptibility is going to be decreased, and as you go on increasing the temperature, the susceptibility or the material converts into the diamagnetic properties. Langmuir's theory of paramagnetism. In the absence of external magnetic field, the dipoles are oriented along different directions such that the resultant sum of all projections of magnetic moments on any reference line is zero. When the external field is applied, the state of magnetization depends upon the following two factors. First, the applied magnetic field. It aligns the magnetic axis of molecules along the field direction. Second, thermal agitation or thermal agitation. It is disorganizes disorganizes the orderly state produced by the applied field. Ferromagnetism. Now, the ferromagnetism. The term ferromagnetism may be defined as a type of magnetism. The term ferromagnetism is defined as the type of magnetism in which a material gets magnetized to a very large extent in the presence of external field. In which a material gets magnetized to a very large extent in the presence of external field. The direction in which the material gets magnetized is same as that of the magnetic field. So ferromagnetism is characterized by the presence of parallel alignment of permanent magnetic dipole moments in single direction. Among the elements, ferromagnetism occurs in iron, cobalt, nickel, Gd and Dy. The important common characteristic of these elements is the existence of partly filled inner electron shell. In a ferromagnetic material, magnetization arises spontaneously over a large region of the material. Importantly, all this happens in the absence of external magnetic field. In this section, we will discuss the temperature dependence of ferromagnetism also. Domain theory and the other aspect temperature dependence of ferromagnetism aspect shall be discussed in the other section. Iron, cobalt, nickel atoms have 24, 25, 26 electrons respectively, and from the third shell have a contribution of dipole moments. The susceptibility is given by the Curie-West law. So, the term ferromagnetic may be defined as a type of magnetism in which material gets magnetized to a very large extent in the presence of an external field. The direction in which the material gets magnetized is the same as the direction of magnetic field. Properties: ferromagnetic materials require a high degree of magnetization in the same sense as the applied field. For some classical examples of ferromagnetic are iron, cobalt, and nickel. These materials attract the line of force strongly and hence permeability values are very high. The value of susceptibility of ferromagnetic is also very large and positive. When ferromagnetic material is placed in an external magnetic field such that the length of the material is parallel to the field direction, a small change in the dimensions occurs. This effect is called magnetorestriction. This effect is called magnetostriction. As the temperature increases, the value of susceptibility decreases. Above a certain temperature, ferromagnetic materials become ordinary paramagnetic, and this temperature is called the Curie temperature. Basic concept of wave and particle nature. Wave particle duality of radiation. For the wave and particle duality, we must to know what is particle, what is wave. The concept of particle is easy to understand because it has mass, it is located at definite point, it moves from one to another place. It gives energy when stopped. The concept of wave is quite difficult compared to particle because a wave is spread out over a relatively large region of space. It is can't be said to be location. Hard to think of mass being associated with it. For simplicity, the wave is specified by its frequency, wavelength, phase or wave velocity, amplitude, intensity. Basic of above concept, it's difficult to accept the conflicting idea that the radiation has dual nature. The radiation is a wave which is spread over the space, so the radiation sometimes behave like a wave and a particle. How is it? Radiation includes visible light, infrared, ultraviolet ray, and X-ray are behaved as wave. Phenomena of interference and diffraction. This is the small introduction about the atomic theory. Uh, it is have a little bit significance when the diamagnetic to understand the diamagnetic or magnetic effect of the element. Because in these phenomena, two waves are simultaneously coinciding at the same position at the same time. Actually, it is difficult for two particles to occupy the same position at the same time. So the radiation behaves like wave. The black body radiation, photoelectric effect, and Crompton effect are established that they are is interaction of radiation energy with matter. Here, radiation interact with matter in the form of photons, so radiation behaves like a particle. Thus, the wave and particle nature is not exhibit simultaneously. De Broglie concept of matter wave. De Broglie extends the wave particle parallelism of the optics to all fundamental things exhibiting independently from other things, fundamental existing things like electron, proton, neutrons, atoms. He suggested that matter has also dual nature, that is wave and particle like radiation. There is a detailed connection between waves and return walk in case of particle also. A moving particle is always associated with the wave and it is controlled by wave. Some as photon is controlled by wave on the concept of wave particle duality. He noted that if the radiation light can act as wave sometimes and can act as particle at the other time, then the material particle should act as wave at the some other times. Hence, the de Broglie hypothesis: a moving particle is associated with wave, which is known as de Broglie wave. Now, the conclusion regarding the magnetic materials. Diamagnetic materials, again I am just reviewing the properties. No permanent dipole of magnetic material is present. The external magnetic field it produces induced magnetic moment. Induced magnetic moment is always in opposite direction of the applied magnetic field. So magnetic induction in the specimen decreases. Magnetic susceptibility is small and negative, repels magnetic line of forces. Diamagnetic susceptibility is independent of temperature and applied magnetic field strength. Relative permeability is less than 1. Example, these are some examples. Superconducting elements in superconducting state. Paramagnetic materials possess permanent dipoles. In the absence of external magnetic field, all dipoles are randomly oriented, so net magnetic moment is zero. In the presence of magnetic field, the material gets feebly magnetized. That is, the material allows magnetic lines of force to pass through it. The orientation of magnetic dipole depends on temperature and applied field. Susceptibility is small and positive. Such as susceptibility is independent of applied magnetic field and depends on temperature. Susceptibility is given by C by T, where C is Curie constant. The spin alignments is random. The magnetic dipoles do not interact. These materials are used in lasers. Paramagnetic property of oxygen is used in NMR technique for medical diagnosis. Example like alkali metal, lithium, sodium, potassium, rubidium, transition metals like aluminum, PT, MnCr. Ferromagnetic materials property possess net magnetic moment, possess spontaneous magnetization. Materials show magnetic properties even in absence of external field. Spontaneous magnetization is the because of interaction between dipoles called exchange coupling. When placed in external magnetic field, it is strongly attracts magnetic line of force. All spins are aligned parallel and in same direction, which shows in figure. Susceptibility is large and positively given by Curie law or Curie temperature law. C is Curie constant, theta is the Curie temperature. When temperature is greater than Curie temperature, the material gets converted into paramagnetic. They possess the property of hysteresis. Materials get divided into small regions called domains. Anti-ferromagnetic material. Property, the spin alignment is anti-parallel manner, shown in the figure. So net magnetic moment is zero because they are anti-parallel. Their effect is cancelled out. The magnetic moment come out to be zero. Susceptibility is small and positive. Initial susceptibility increase with increase in temperature, and the beyond Néel temperature, the susceptibility decrease with temperature. At Néel temperature, susceptibility is maximum. Example: iron oxide, manganese oxide, and salts of transition elements. Ferromagnetic materials. Property, special type of anti-ferromagnetic material. The spin alignment is anti-parallel but different magnitude, as shown in the figure. So they possess net magnetic moment, also called ferrites. Susceptibility is very large and positive. Example: ferrous ferrite, nickel ferrite. Domain theory of ferromagnetic material. So, as of now, this is enough for today, and we will continue the lecture from domain theory of ferromagnetic materials. And in continuation to this topic, we are going to start with superconducting materials or superconductors, or the introduction of or the difference between the insulator, conductors, and semiconductors. Then move to the superconductors, and then we just do some questionnaires or quizzes. So thank you all for today's lecture.